Good afternoon, students. Myself, Dr. Sandeep Gupta. I am assistant professor in Ajay Kumar Garg Engineering College, Ghaziabad. I will take the topic of chemistry. This is molecular orbital theory and its application. As you all know, that this theory was developed by Honds and Mulliken. By this theory, we would like to explain the diagrammatic representation or molecular orbital diagram of hydrogen, nitrogen, oxygen, which is diatomic molecule, homodiatomic molecule, and HF, NO, CO, which are heterodiatomic molecule. So the postulates are written here, but I would like to explain you through some visual representation. So, as you all know, that the atom contain electron, and this electron which is present in outer shell, this is called valence electron. And this valence electron of this atom and valence electron of another atom, they overlap with each other, they make bonding, and by the bonding they form molecule. So how this molecule is going to be formed, this can be explained by these postulates. So if this is one energy level of one atom, this is one energy level of another atom, when they combined, they will form new energy level which is named as molecular orbitals. So these are the atomic orbitals, and when these atomic orbital overlap with each other, combined, they will form new energy level which is named as molecular orbital. So if I am taking example of this atom, here this electron is strongly attracted by one nucleus. But when the overlapping occurs, the electron can be attracted by more than one nucleus and it is become polycentric. Another thing, the number of atomic orbitals, for example, here I have two atoms, energy level means I have two atomic orbitals. So the number of atomic orbital are always equal to number of molecular orbital. So if there are two atomic orbital, then we will get two molecular orbital. And in these atomic orbital, if the number of electrons are maximum number of electrons which can be remain in this energy level, these are two electrons with opposite spin. Suppose we have two electrons here, two electrons here, then the filling occurs, two electron here and two electron here. So by this way the filling occur. These two energy levels which have comparable energy, that have also same orientation, the overlapping is possible only when the atomic orbitals have comparable energy as well as same orientation, which can be explained by LCO method. I will discuss in brief LCO method. So if one s orbital which is spherical, one s orbital and another s orbital is going to be overlap. So this overlapping may be like this, because we are assuming that the electron is behaving just like a wave. So these two waves overlap with each other, and this overlapping gives the constructive overlapping. So once these two atomic orbitals constructively overlap with each other, then what happened? This is one atomic orbital, this is another atomic orbital, and the probability of electron here get increased. So the probability of electron in this energy level get increased. So electron will, the probability of electron in this region will increase, and this type of energy molecular orbital or energy level are called bonding molecular orbitals. And when the opposite, the wave functions are going to be overlap, means if the one wave is going in this direction and another wave is going in this direction, then the overlapping will be in form of destructive overlapping, ungyred overlapping, negative overlapping, in which the magnitude of the wave function get reduced and the resultant molecular orbital, like this and you can say this, they will become, the electron here will move to maximum distance and it will show like this. Okay. So this type of molecular orbital is named as ABMO. So this all thing we will discuss in linear combination of atomic orbital. So this is only a hint for linear combination of atomic orbital. Now I am going to discuss the molecular orbital. So this bonding molecular orbital, which is generally named as highest occupied molecular orbital, and the ABMO, which is termed as lowest unoccupied molecular orbital. So whenever the overlapping occurs, the atoms will make one bonding molecular orbital and another energy level, which is called anti-bonding molecular orbital. The energy of bonding molecular orbital is quite low, hence it is very stable, while the energy of ABMO is very high, that's why it is unstable. So if we will discuss the stability part, then if the electrons are present in bonding molecular orbital, then the molecules will be stable, and if the electrons are present in anti-bonding molecular orbital, then the molecule will be unstable. So this is the representation of this. Suppose I am taking the example of hydrogen. These two hydrogen atoms get combined with each other. It is forming, if the wave function of this, suppose this is the wave function of this and this is the wave function of this. This is psi A, this is psi B, psi is the wave function, and if these two atoms are constructively overlap, then it will form bonding molecular orbital, means the resultant of this bonding molecular orbital get increased. The magnitude of this resultant of this bonding molecular orbital get increased. And if these two wave functions negatively overlap with each other, suppose as I earlier told you that this is the wave function of this atom this is the wave function of this atom. This is psi A, this is psi B, and if they are negatively overlap with each other, then the resultant wave will be lower in magnitude, and this will form anti-bonding molecular orbital that have one node. Okay. Same in case of P, we have P orbital. P have 3 subshell, X, Y, S, Z, and this Z is basically by default axis of this P shell, and once the P orbital will overlap with each other, then this is the constructive overlapping, where these two will overlap and the probability of electron in this region will increase. Hence, this area will be high, and this is called bonding molecular orbital. While if the waves are in, you can say opposite wave functions are here, then the electron present here, they want to live maximum distance, they want to show maximum distance. Hence, this probability of electron in this area will reduced. Hence, this region will, it will become very, you can say the magnitude of the resultant is very less here. Similarly, here we can say that if the p orbital is overlapping in a different axis, which is x-axis, then during the constructive overlapping, this region will overlap with each other, and the probability of electron get increase here, and probability of electron increase here. That's why this molecular orbital is named as bonding molecular orbital, while this is named as anti-bonding molecular orbital. So, the next postulates of this MOT is during the molecular orbital formation, the filling of electron is done as per Aufbau rule. What Aufbau rule is saying? The electron orbitals will be filled in a higher energy. Means first lower energy orbital will fill, then higher energy will fill, and then higher energy will fill. So, the electron filling in the orbital will be in a manner of 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, and so on. But as in our syllabus, we will discuss only hydrogen, nitrogen, oxygen, carbon monoxide. So, we will discuss up to 14, 15 electrons that we will fulfill here. What is this? These are the principal quantum number, and what is this? This is azimuthal quantum number. So, if I want what is the energy of this shell, this region. So, this is basically n plus L. This region is, the energy of this region is basically n plus L. N is 3 and L for P, this is for S, for P, for D, for F subshell. So, for P we have 1, value of P for L is 1. Hence, we have 3 plus 1 means 4. So, the energy of this region is 4. Okay, and energy of this region is basically 4 plus 1, which is 5. So, Aufbau rule is saying the electron first reaches to lower energy, which is 4, and then next orbital will be filled, which is 5, whose energy is 5. So you can say the filling of electron will be done in a increasing order. That's why whenever we will make molecular orbital diagram, we will use this arrow sign. Means the energy of this region is very low while energy of this region is very high. Similarly, during molecular orbital formation, the filling follows the Pauli's exclusion principle and Hund's rule. If we will discuss the bond order, so the bond order is basically number of electron in bonding molecular orbital minus number of electron in anti-bonding molecular orbital divided by 2. Okay. So we will take more examples. For just for remembering, we have this formula. Just keep in your mind and I will discuss further. If the bond order is high, then there is a difference, there is a inverse relationship with the bond length. Bond order is high, then bond length will be low. Okay. And if the molecular orbital contains unpaired electron, then the magnetic behavior of this molecule is paramagnetic, while if the all molecular orbital contains paired electron, then the nature is diamagnetic. So we will discuss one more thing later on. So here I am going to discuss by taking one example of hydrogen. So by making the molecular orbital diagram, first we have to write down the electronic configuration. For example, this is the hydrogen molecule. So electronic configuration, the atomic number of hydrogen is 1 and its electronic configuration is 1s1. So for making molecule, we must have 2 atoms. So another atom will also participate here and the electronic configuration is 1s1. Okay. So when these 2 atoms overlap, one bonding molecular orbital will form and another will anti-bonding molecular orbital will form, ABMO will form. So when S and S overlap, when the S orbital and S orbital overlap, then what kind of bond will form? Sigma bond will form. So when these 2 atoms will overlap, then sigma bond will form and energy of 1s1 will, this is named as 1s and another one is sigma star 1s, where this is BMO and this is ABMO. Now how much electron will fill? We have 2 electrons, that's why we will fill 2 electrons here. And as per MO postulates, the number of atomic orbitals are equal to number of molecular orbital. So if there are 2 atomic orbitals, then there are 2 molecular orbital. So you have to write down this energy level also, sigma star 1s 0, and this 0 represent that there is 0 electron in this energy level, this molecular orbital. Okay. So this is the molecular orbital configuration of this hydrogen. So what we will do? Sigma 1s2 and sigma star 1s0. Now if I want to calculate the bond order, so what is the bond order? Bond order is basically half of number of electron in bonding minus number of electron in anti-bonding. The number of electron in bonding molecular orbital is 2 and number of electron in anti-bonding is 0, and this is, the value will become 1. Okay. So this is basically The bond order of this hydrogen molecule is 1. Now, what is the magnetic behavior of this hydrogen molecule? Look at here. If all are paired, all electrons are paired in molecular orbital, then this is called diamagnetic, while if unpaired electrons are present, then it is called paramagnetic. So, right now the magnetic behavior of this is diamagnetic, while if we have one more atom, suppose I am going to write down the electronic configuration or molecular orbital configuration of H2 minus, means one electron I would like to add, then what happen? I will add one more electron here, okay, H2 minus, this one more electron here, okay. So, due to this is presence of unpaired electron, the magnetic behavior will become paramagnetic. So, the soldier which is jumping, he is only single. So, if the unpaired electrons are present, it is paramagnetic. If paired electrons are here, then this is diamagnetic. Okay. Now, I would like to discuss one more thing, that generally it confuses, that this is minus charge. If where we will increase the electron, in this energy level or in this energy level. So, you can increase electron any of the energy level. For the sake of example, I am increasing here, okay, because if you will see the postulate, then you can see when the molecular orbital form, the atomic orbital loses their individual identity, means there is no existence of atomic orbital after the formation of molecular orbital. Once the molecular orbital will form, there is no existence of this. So, whether you will increase electron here or here, it doesn't affect the overlapping, okay. And this sign is basically representation of the energy of this is lower, while the energy of this is very high, okay. So, I am going to discuss one more thing, this hydrogen minus. So, for hydrogen, we have this atomic orbital, these square boxes are atomic orbital. When the energy and orientations are same. So, energy are comparable and orientations are same, and by this way, this hydrogen is going to overlap this hydrogen plus. That's why one electron have been missed from this place, and because two atomic orbital are overlapping, two molecular orbital will form, okay. So, there is only one electron, this is the one electron, s and s orbitals are overlapping, that's why sigma bond will form, and its molecular orbital configuration is sigma 1s1, comma sigma star 1s0, okay. And the bond order is basically half of bonding minus anti-bonding, okay. So, half of 1 minus 0 is basically 1 upon 2 means half. So, its bond order is half, and the nature of this is basically paramagnetic. And H2 minus is basically one electron is added. So, as per thumb rule, what we are doing? We are increasing electron in atomic orbital, which will be disintegrated later on. So, there is no effect in molecular orbital, whether you will increase electron here or here, okay. So if I am increasing electron here, S2 minus, 1 electron is increased here, then total electrons are 3. So maximum number of electron in this orbital are 2 which have opposite spin. So there are 2 electrons that have opposite spin, and remaining 1 electron will reach to here, and the bond order of this is basically 2 minus 1 over 2, which is 1 by 2. So this is also 1 by 2. This is its bond order is also 1 by 2. Its bond order is also 1 by 2. Both the atom will exist. Both the molecules will exist. Now, which is more stable? So, those molecules will more stable which have no electron or less electron in antibonding molecular orbital. So, here there is no electron in antibonding molecular orbital. That increases its stability, while presence of the electron in antibonding molecular orbital reduces the stability, because the energy of this will very high. So this is helium and helium-2. Just have a look of this also. Helium, for helium, we will write down the electronic configuration first. So this is 2, 1s2, another helium atom. This is also 2, 1s2. When these two overlap, sigma bond will form and one bonding molecular orbital will form and another anti-bonding molecular will form, and the total number of electrons are 4. So 2 here, 2 here. That's why sigma 1s2 and sigma star 1s2. The electronic molecular orbital configuration is this: sigma 1s2 and sigma star 1s2. So here this is for helium, plain helium, okay. But for helium plus, what we have to do? We have to reduce 1 electron, and if 1 electron will less, then the bond order will become 2 minus 1 upon 2, which is half. And in case of this is helium-2, this is basically 2 minus 2 upon 2 means it is 0. So if the bond order will become 0, it says that the molecule cannot exist in the nature. So this helium cannot exist as a molecule form, while He2 plus can exist in a molecular form. So here I am going to discuss one more example of this lithium and beryllium. So for lithium, where 2s and 2p orbital also participated. So for lithium, atomic number is 3. So what happens? Its electronic configuration is 1s2, 2s1, okay. And another lithium, it can be written as 1s2, 2s1, and its molecular orbital configuration, because these two energy level will overlap, form one bonding, one anti-bonding. These two energy level will overlap, form one anti-bonding and one bonding, okay. So 1s2 means sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Why I am writing sigma only? Because s and s orbitals are overlapping, and when the s and s overlap are overlapping in this manner, then sigma bonds will form, and if p orbitals are overlapping with each other, then one axis is this and two axis is this. So one sigma bond will form and two pi bonds will form. So here only sigma bonds are forming, hence we are writing sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Total number of electron 2 to 4, 2 electrons, 2 electrons and 2 electrons 0. Okay. So just have a look of this lithium. Here 1s, if we will write down the molecular orbital diagram, then I will write down atomic orbital, which is represented as a square boxes. This is also atomic orbital of lithium. Okay, lithium atom. This is also lithium atom. Okay, this is 1s energy level where 2 electrons are present. 1s energy level where 2 electrons are present. Another lithium atom, 1s orbital where 2 electrons are present. They overlap with each other, form bonding and anti-bonding molecular orbital having 2 electrons, 2 electrons, and this is called molecular orbital, which is basically sigma 1s2 and sigma star 1s2. Sigma 1s2 and sigma star 1s2. Okay. Next, this 2s energy level will overlap with each other. So this 2s have only one electron here, one electron here. So in this 2s energy level, only one electron are present in atomic orbital. 2s of this energy level also contain only one electron. When they overlap with each other, they will form sigma 2s molecular orbital having 2 electrons. And here there is no electron, hence sigma 2s 0. So this is the molecular orbital configuration, while this is the molecular orbital diagram. And this arrow, you have to draw this arrow because it is showing the energy of this is lower than energy of this. So by this way we can draw the molecular orbital diagram of lithium. Just write down its bond order. So for the bond order, we have number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. So total number of bonding electron in bonding molecular orbital 2 plus 2, this is 4 minus 2, this is anti-bonding, upon 2, it means 1. So the bond order of lithium is 1. While in case of beryllium, you can just do it yourself. You can say there is total number of electrons are 4. So for beryllium, you have atomic number 4 and 4 can be represented as 1s2, 2s2. Another beryllium can be represented as 1s2, 2s2, and its configuration can be written as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So if you will draw the MO diagram, this is basically 1s energy level, atomic orbital of beryllium, atomic orbital of beryllium. This is 1s, this is also 1s. It contains 2 electron, it contains 2 electron. They overlap with each other, form one bonding molecular orbital, one anti-bonding molecular orbital. Here 2 electrons are here. Here also 2 electrons are present. These 2s energy level will overlap with each other, form 2s2 and 2s2. So the net result, if you will see, this bonding minus anti-bonding 0, bonding minus anti-bonding 0. If you will see bond order, so 2 to 4 minus 2 to 4 upon 2 means 0. So this bond order is 0. It means it cannot be exist in a nature as a molecule. So this is very important diagram of nitrogen. So for the nitrogen and oxygen, we have a little bit change in configuration. Just have, when we go from boron to nitrogen, due to sp mixing, what happens? This energy of sigma 2p is increases, while when we move from oxygen to above, the sp mixing get reduced and the energy of this sigma will reduced. Hence, the configuration from boron to nitrogen is different, and from oxygen and above it is quite different. So, here I would like to explain this thing, that due to sp mixing, what happens? The energy of this sigma 2p molecular orbital get increased, hence it is quite above the pi orbitals, while up to you can say oxygen, or you can say oxygen and above, what happens? No sp mixing is going on, hence the energy of sigma 2p get reduced and it is quite earlier. So, if you will see what I am trying to say, this is this configuration. So, up to nitrogen, okay, what happens? The molecular orbital configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p x, y, z, whatever you can write down it here, pi 2p y 2 is equal to pi 2p z 2. Then electron will move into sigma 2p x. I have already told why this happened, because of sp mixing. The energy of this sigma 2p get increased, hence electron will come here. Then electron will move into pi 2p y, pi 2p z and sigma 2p x. This can be rewrite as you can, but by default the molecular orbital of p axis is z. So, whatever you can write down x, y, z, y, z, x, it is okay. While for heavier molecule, means oxygen and above, what happens? The configuration will be like this: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z. Okay. Why this happened? Due to here the molecules like oxygen, it is compressed and the energy level of these molecules get come closer to each other, hence sp mixing will finished and sp mixing will not done, and due to this what happens? Electron will, energy of this sigma 2p z will get reduced. Then electron will come in sigma 2p z 2, then pi 2p x, pi 2p y and pi star 2p x, pi star 2p y and sigma 2p z. So, basically this is base of molecular orbital theory, where up to nitrogen this will sigma 2p x, sigma 2p y, sigma 2p z, whatever you want to write, it will come at high energy level, while up to for oxygen and above, what happens? The sigma 2p z will come before pi orbital. The filling order will be this. So, here I want to show the molecular orbital diagram of nitrogen. So, for nitrogen, what happens? If we will write down the nitrogen, so atomic number of nitrogen is 7. So, its electronic configuration is 1s2, 2s2, 2p3. Okay. So, 2 nitrogen will meet, overlap with each other and form molecule. So, here also 1s2, 2s2, 2p3. So, the configuration will be total electron 14, and for 14 configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p xyz, pi 2p y2, pi 2p z2, sigma 2px 2. So, total electron here 2, 4, 6, 8, 10, 12, 14. So what about this? They will become 0. Okay, they will become 0. So this configuration you will write here, and by this configuration you can make this diagram. So below this 1s orbital, this is 1s orbital, which can be represented as kk shell or kk orbital. So kk I am skipping, this kk I am skipping. For 2s2, this is energy level of 2s of 1 nitrogen. This is of 1 nitrogen, atomic orbital of 1 nitrogen, and this is 2s. When they overlap each other, they will form nitrogen molecular orbital. 2 electrons here, 2 electrons here. This is bonding molecular orbital, this is anti-bonding molecular orbital, and by this way this overlapping occurs. For this p orbital, we have px, py, pz, px, py, pz, and they will overlap in this manner that first pi orbital will fill. So this pi orbital will fill. So in pi orbital 2 electrons comes, total electron are 6, 1, 2, 3, 4, 5, 6. So first electron will go in pi orbital, and then electron will go in sigma orbital, and the rest are 0. Okay. So in anti-bonding molecular orbital there are no electron, but we have to write down it because number of atomic orbital are equal to number of molecular orbital. There are 1, 2, 3, 6 orbital. So total atomic orbitals are 6. Hence molecular orbital will be 6. 1, 2, 3, 4, 5, 6. That's why we have to write down it. And this energy sign we have to show that the energy of this 2s is lower than this energy of 2p. Next, for this oxygen, I am also skipping kk shell. Okay, this kk shell I am skipping. Now what happens? Electron will reach first in sigma 2p and then pi 2p. So configuration will be quite different than nitrogen. In nitrogen, first electron are going in pi orbital and then sigma orbital, means energy of sigma orbital due to sp mixing will become higher in nitrogen, while for oxygen sp mixing will get reduced or no sp mixing will occur. Hence the energy of pi orbital will increase. So like nitrogen, we will make this 2s of oxygen. They will overlap, oxygen molecular orbital will form, total 4 electron, 2 in bonding, 2 in anti-bondings. Total, what is the oxygen atomic number? It is 8. So 1s2, 2s2, 2p, 4. So in p orbital we have 4 electron, 2 to 4, 2 to 4. So when they 8 electrons will fill in molecule orbital, then what happens? First it will reach in sigma 2, then it will reach in pi orbital 2, 2, and then last 2 electrons 2 to 4 to 6, remaining 2 electrons of this 2p will reach in anti-bonding pi orbital. So the configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, and then pi star 2px1 and pi star 2py1. I am trying to write down here 2, 2, 2, 2, 1, 1, 1, 1, 2, 2, and this is 0. Okay. So if you will see here, the electrons are unpaired, hence this is basically paramagnetic. So the nature of oxygen is paramagnetic. In case of NO, this is heterodiatomic molecule. There is a big difference in energy difference in between oxygen and nitrogen. Oxygen is more electronegative, hence it will attract towards, you can say, nucleus. There are more proton, there are more electron, there are more attraction force, hence it will quite lower, while there it is quite higher. The energy of this nitrogen is quite higher, while the oxygen is quite low. So, for nitrogen, NO, we have atomic number of nitrogen is 7. So, this is 1s2, 2s2, 2p3, and for oxygen it is 8. So, 1s2, 2s2, 2p4. So, for NO, what happened? Total electrons are 15. So, we will follow the configuration above oxygen. So, for above oxygen, what is the configuration? Sigma 1s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p xyz, whatever you want to write down it, 2p x, then pi 2p y equal to pi 2p z. This equal to means the energy of this pi 2p orbitals are equal. Now, electron will go in pi star 2p y, pi star 2p z, sigma star 2p x. Total electrons are 15, 2, 4, 6, 8, 10, 12, 14, and 1 is 15. Okay. So, this is the molecular orbital configuration, and I am trying to write down here the molecular orbital diagram by skipping this KK shell. So, in bonding molecular orbital and anti-bonding 2s, we have 2 electrons. This is atomic orbital of nitrogen. This is atomic orbital of oxygen. They will overlap, they will form NO, and total electron 4, 2 in bonding, 2 in anti-bonding. So, this is clear. Now, for p orbital, there are 3 electrons in p, px, py, pz, px, py, pz. In oxygen, there are 4 electrons. They will overlap, and due to sp mixing, no sp mixing, electron will go first in sigma 2px 2, then electron will go in pi 2p 2, pi 2p 2. Okay, and one electron will go in anti-bonding 2p xyz, whatever you want to give it terms. Okay, but by default, the electrons will, the p orbital will be pz orbital. So, electron will go in pi 2p y. So, what about this? This is 0, 0. So, we have to write down 0, 0. And the nature of this is also what? Paramagnetic. So, in case of HF, what happens? The energy of 1s of H is very high, that it cannot overlap with the 1s of fluorine. Even the energy is too much high that it cannot overlap with 2s of fluorine. Okay, and now it will overlap with the 2p orbitals. So, for HF, what happens? For HF, what happens? H is 1, 1s1, and for fluorine, it is 9, 1s2, 2s2, 2p5. Okay. So, 1s will not overlap with this, 1s will not overlap with this, 1s will overlap with this. So, when s orbital and p orbital of same axis, this is s, suppose this is x axis and this is px orbital, they will overlap. What happens? It will form what kind of? It will form sigma bond. Hence, electron will go first in sigma 1s, 2p, total electrons are 2, okay, 2px, 2. While this is basically non-bonding electrons. They will not participate in bonding. So, by this we have total how much? 1, 2, 3, 4. Total 4 atomic orbitals are overlapping. Hence, okay, total 4 atomic orbitals are here, but overlapping is going on in between this and this. Hence, total 2 atomic orbital. So, one is bonding, one is anti-bonding. So, anti-bonding will be sigma star 1s 2px star 0. So, its configuration will be entirely differ due to exception. Its configuration will be HF molecular orbital configuration sigma 1s 2px 2 sigma star 1s 2px 0. So, this is the molecular orbital configuration of HF. You can just go to these books, and these are the various books where you can profoundly study it. Thank you very much.